Hello, everyone. Thank you for attending today's first seminar, Shields Up, Reducing Risk with Microchip Technology Security Solutions. This is the first of many seminars we'll be broadcasting over the next year, one every 2 weeks. We've got 4 up on our website that you can register for. Today we're going to be talking about RISC-V security, multi-zone security, making RISC-V the most secure platform ever, and we'll do a short little introduction to PolarFire SoC, which is the world's first RISC-V SoC FPGA. My name is Tim Morin. I'm a technical fellow at Microchip Corporation. I came through the Microsemi FPGA business unit acquisition, and I'd like to introduce to you Cesare Garlati, the CEO and founder of RISC-V Security, and he'll be talking about what their offering is and how it can provide security to Linux platforms, embedded platforms, and SoC FPGA platforms. Cesare, take it away.
Thank you, Tim. Thank you for having me. The topic of today is really the first part of a 2-part series. The second part will be broadcasted first week of December, if I'm not wrong. Today we will be focusing on how to secure RISC-V systems at an MCU level. And so what I'm going to do is to share some basics about the problem and how RISC-V eventually addresses this problem. We will get into Linux enclaves in the second part, which is again early December. So this is the way we see the embedded computing thread model. It's really a system where sharing is the norm. And typically, if you have a connected devices, and that's what you see on the left side of the slide, you will have different functional blocks. And at the hardware layer, these blocks get merged, fused into one single application. And because the application is monolithic, all of these key components, functional components, share the very same resources. So typically, if it is a connected device, it will have a network stack. And whether that's TCP/IP or Bluetooth or anything else, doesn't matter. That's quite a bit of software that interacts with quite a bit of hardware there. If there is security, there's probably TLS. That's how we know security today in terms of communication and encryption. And TLS requires secrets, requires a root of trust. So the root of trust itself, with not just the hardware, but the software that runs it, which includes the text segment, the program, but also the data segment, which is the state of the program the moment it is processing secret or, in any case, confidential information, is eventually shared with the rest of the system. And now, crypto is quite complex. No one really writes crypto libraries, and so typically these come in as a third-party object or library. And of course, there is user code, because the box in the end has to do something. And that user code typically involves also a real-time operating system, if not bare metal drivers and so forth. And now we are familiar with the process. We compile, link everything in one single monolithic piece of software, and everything ends up sharing the very same memory structures. Well, real-time or MCU-based systems lack the basic hardware security. Primitives like the memory management unit and the relative virtual memory. And so it's clear that any line of code, intentionally or accidentally, can break the confidentiality, integrity, and most importantly, for safety-critical application or availability of the system. Any line of code can potentially just loop or get the processor into exception and basically kill the system as a whole. And if you're thinking about Linux being the solution here, well, Linux obviously has a kernel that supports MMU, memory management unit, and a relative virtual memory. But there is a couple of problems, big problems there. So the first one is that Linux kernel starts with 17 million lines of code, and the kernel itself is not really enough to do anything. So typical systems that run Linux embedded have at least tens of megabytes of code, okay? And that's definitely an attack surface that is simply not acceptable in some safety-critical applications. And Tim will share some more details about the use cases later in the presentation. Let's not forget, by the way, also the known free kernel drivers. And so for people who are not super familiar with this, Linux has a modular architecture in terms of drivers, and drivers are the pieces of software that basically make the hardware work. But while Linux and all the components of Linux systems are typically open source, and so in theory, well, most of the key drivers for Wi-Fi, for whatever is the situation of the system, are in fact not exposed in terms of source code. And that's a major security concern, especially when we extend this not just to the drivers, but basically to any software that runs into any box. It's very unlikely these days, given the complexity of requirements, that any single vendor, for as large as it is, can really build all the software in-house. And so the supply chain issue becomes really relevant, because any single system designer will end up integrating third-party libraries, and whether they are open source or proprietary black boxes, binaries, doesn't really matter. The problem is that the supply chain introduces at least 100+ libraries in a typical IoT stack, and it is due to a third-party vendor encapsulating libraries themselves and so forth. And final point that I wanted to share with the audience today is the cache, the big issue of side channel attacks. And Tim has a few slides in the end that will show how the PolarFire FPGA SoC is in fact designed to minimize or eliminate this issue. But let's not forget, data is not in the core, goes through the core, but it's somewhere else. That somewhere else is more likely to be caches. Very good. So I think the point, the problem statement is really that embedded computing as we know today, either on MCU or Linux, is definitely not secure enough. And so here is what RISC-V offers in terms of security primitives or security building blocks. For people who are not super familiar with RISC-V, I invite you to check the RISC-V Foundation webpage. RISC-V is an ISA, an instruction set architecture. It is not a chip. It is not a vendor. It is not a school project. It's a contract in between hardware and software. And so this contract includes these clauses, right? These entries. So one is the privilege levels. Nothing new to RISC-V. RISC-V has 4. One is called machine, is the highest level of privilege, and is always present in any RISC-V core. If the core has Linux, and therefore, when I say Linux, I mean a rich operating system able to drive, capable to drive an MMU, that's probably a situation where the supervisor mode, or S, is included. Now, there's also a higher level to the supervisor, which is the H, or hypervisor. There are 2 bits, so you think about with 4 different combinations there. The hypervisor specs are in the making, a lot of work, a lot of interest, but as of today, there's really no standardized way to do hypervisors yet. And then there is the user or application level. This is typically used by Linux user land in a Linux situation, but very interesting, can be just combined with the machine mode, which gives up for a very interesting deployment scenario, which is a secure embedded system that doesn't have an MMU, that doesn't run into all the issues of Linux, but at the same time is as secure, if not more secure, than the traditional approach. And when I say more secure, meaning less attack surface. And so here are the 3 rings or 3 privilege modes. If you have M, only M, well, there's no way you can secure that system at a hardware level. Separation is not possible. But if you have M and U, which I see more and more, that's ideal for secure embedded systems that have an MCU, or to secure the MCU that is included in a bigger system that eventually has additional Linux-capable cores. And that would be eventually the number 3, where machine, supervisor, and user mode are all 3 present. Now, as a complement to privilege mode, there is something in RISC-V which is standardized at the core level. This is very important. This is in the core, and it's standard, 100% standard, and it's called PMP, or physical memory protection. So without going too much into the details on how it works, the key concept is very simple, right? This is a peripheral, so something memory mapped in other systems. In this case, these are registers inside the core itself that are accessible only through the machine mode or through delegation through the supervisor mode. And what can be done is to define a set, a number of memory contiguous spaces. And this is not just about securing memory, this is about securing any memory mapped resource, including all the peripherals and any kind of data that is accessible through the interconnect to the bus. And whenever there is a policy enforced there, a value loaded up, well, the system in real time, the hardware checks whether the policies are respected. Otherwise, there is an exception. So this is as solid, as resilient as you can get, because it's really delivered by basically a set of gates, to make it very simple. Okay, so one thing is to have primitives, and one thing is to actually make them work, right? And so here is what multi-zone trust execution environment does. Leverages, orchestrates those primitives and many other pieces of the system, really, to develop something like this. And what you see on the screen, it's the equivalent of the application, the use case that I showed you in the first slide, but this, in this case, is secure in the sense that provides isolation. You can look at these vertical columns as zones. We call them zones. You can look at them as containers, whatever name you want to pick. But the whole idea is that they are physically isolated. The core, once the policies are set, would prevent any leakage or any cross-reference or any damage in one zone to spill to the other one. And so typically, and we have one slide coming up very soon, in zone we would put the root of trust with eventually secrets and path and whatever is required to get that crypto working. The network stack was definitely separated because that's what's exposed to a remote attack. That's the most likely to be attacked and eventually breached, but that breach will not spread to the rest of the system. Over-the-air updates is a requirement you see more and more. If you want to do sound over-the-air updates, you have to have a completely separated stack. Otherwise, you use the faulty stack to update a new one, and you are just attacking the system remotely, basically. And of course, then you'll have any kind of combination of rich operating system or real-time. And there are only 5 here because that's a slide, but there can be more there. And so just to give an idea what's possible with these 5, if properly orchestrated, it's multiple, equally secure zones, so there's no concept of a secure world and non-secure world. Either you get separation or you don't, so they are all separated, they are all secure, they all run in user mode. And anything can be mapped to those zones, RAM, ROM, I/O, and their handlers. It's enforced by the hardware, so you can't get any stronger than this, but it's very flexible because the policies are defined via software. And policies include read, write, and execute. So it's not just being in or out, any kind of possible combinations of these policies. Super lightweight. In fact, the code base is less than 2 kilobytes, and this allows for formal verification, which is definitely what is needed in this case. As of now, Multizone is offered as open source API, so free and open standard. The commercial implementation provided at Multizone is the only one available in the market as of today. It's designed for mixed criticality and purpose-built secure systems. It's a lot to do with L1 and L2 caches. We'll see more in a second. And with this kind of solution, basically any RISC-V core can be covered. So it scales from single core 32 bits with 16 registers, which is called the RV32E, to multi-core SMP Linux 64 bits, and who knows, 128 coming probably soon. Super easy to use. There's no coding is required, no files to link, to change, to nothing all over. It's a tool chain extension, and we'll see this in a slide. No need to rewrite software. So this system runs binaries. So if you have a binary, it will run it in a secure container. And as I say, there's a commercial software license available for commercial entities. Otherwise, everything I'm showing to you is on GitHub. Please go grab it, play with it, and let us know if something is not working, okay? And no royalties ever. Okay, so here is what we did based on the microchip, microsemi, PolarFire. So as I said, all of this is real, is working, it's on GitHub. If you are lost finding the pieces, let me know, send me an email, send him an email. But here is a typical system. You have some hardware that on one end connects over an untrusted link to the internet, to the cloud. And on the right side, in this case, we have a little robotic arm, it's a toy, and then we have a local console. The whole idea is that this is a typical embedded connected device. If you want to call it IoT, that's fine. But the pieces are there and they're typical of any application that I've seen so far. So let's build a system together. So what we do on the PolarFire, on the RISC-V core, we make sure there is PMP, physical memory protection. As I say, this is hardware, it's standard, it's there. If it's not there, you don't have a secure system, so there's no magic you can do anyway. Now, we add the multizone layer, which is this 1.6 kilobytes of running code, to the M mode, the highest level of privilege. And that's what controls and keeps and maintains separation and provides inter-zone communications across the zones. Now you understand, there's no cross-reference in between zones. They are compiled, linked separately. They cannot communicate to a traditional API schema where you put something on the stack and then you get something back or on the hive. It has to be done in a very different way, which is through messages, which is not different than any other, I would say, TCP IP-oriented kind of communication. It's just super lightweight because this, as I say, fits 1.6 kilobytes of memory. The robotic arm, or your protected piece of machinery, is controlled via a real-time operating system. In this case, we use FreeRTOS. FreeRTOS runs in user mode, which means that it will not be able to cause damage to the other zones. It's protected, it's secured. And FreeRTOS uses, as I said, mapping is all extends to the hardware, uses the GPIO lines, because that's what we use to control the robotic arm. In the second zone, we put a full-blown, complete TCP IP stack. All of this is open source, is GPL, and then dual license for commercial use. So this is state-of-the-art. This is not a school project. This is as real as it gets, okay? So in this case, we use Pico TCP. You feel free to change with your TCP IP stack of choice. What's important is that this block drives the Ethernet port, as you would expect. And then in the third zone, we have the root of trust. In this case, we use a full stack provided by Wolf SSL, which is the de facto standard for embedded. Wolf SSL is a commercial vendor, members of the ecosystem of Microchip as well. The hardware is used in this case is OTP or PAF or fuses. In our case, we are just storing certificates in flash because, as I said, it's partitioned. And for as far as this kind of threat model, it's secure. In the fourth zone, we have bare metal console. They just allow to exercise the security features and see how strong is the separation. So here is how all it comes together. It's very simple. So if you can write that file that you see on the left side of the screen, you can secure the system I just showed you in the first slide. Okay? So this is not a piece of the file. This is the whole file. So this is the whole complexity any developer, any system designer will always be exposed to. There's nothing more, nothing less you can do. And so as far as the attack surface, this is extremely resilient, right? No coding, no debugging. If you can declare, if you can define those policies, you can secure your system. I'm just commenting on zone number 1. We don't have time to go through all of them, but it gives you a sense. So zone number 1 is what runs FreeRTOS and moves the robotic arm. And so, well, there is interrupt number 16 mapped to that zone, which in this case, it's a push button that turns on LEDs, nothing to do with the robotic arm really. But you see that zone 2 has different interrupts mapped to it. The concept is that interrupts envers are executed in the context of the zone. And that's for security, right? You don't want to execute drivers or interrupt handlers at the highest level of privilege, otherwise you break the separation model. And so zone number 1 has some flash program, some program in flash. The policy is read and execute, that's the first line. It's 64 kilobytes and starts from 2041, whatever is the address there. Now, the second entry there is for the RAM. That's data, different address, different size. That's basically same concept. And the other 3 are pieces of hardware. Those are peripherals that are mapped to that zone. Once the file is written, and there's this little utility, which is a toolchain extension that runs at the end of your traditional development cycle, that picks all the binaries for the zones. And as I said, again, these are fully linked, totally independent binaries. They can do anything, written with different programming languages. They can be completely broken eventually. Doesn't matter. The system will keep working. Every zone is guaranteed to run. There is a preemptive kernel scheduler built in. The nano kernel is injected, which is super thin, and those policies. The whole file is signed and ends up in the secure boot firmware. That's really how it works, and I think this is really what every developer would like to see, basically. This is the last slide, just to give you a sense of if you want to interact with an API, what the API looks like. This is open source, permissive licensing, ISC, is on GitHub. Please do your own implementation if you feel so. If you are in a commercial context and you don't wanna take the risk and the time, we offer the commercial version. And so these are hardware threat management primitives. Yield is about handing over the CPU to the next zone, while waiting for interrupt, WFI, it's a primitive, it's an instruction really in this file, it's the low power mode. And obviously the system is multitask, in this case, multi-zones. And so when all the zones are waiting for interrupt, the system actually goes in low power mode, waiting for interrupt. The next two are the basic, the primitives for inter-zone communications. Very simple, send and receive, then you pass the pointer of some local data, local to the zone, and the zone that you want to send or receive from. Please pay attention, this is high security. You don't specify the source of the request, and that's the way you cannot spoof it. The system knows where the requests are coming. So this is as solid as it can get. Something about setting interrupts or traps. One is synchronous, the other one asynchronous, and enabling or disabling interrupt. Nothing really special. This is what you would expect. What's in this file and what you would expect from any processor, really. Multizone provides soft timers, typically, let's say in this way. So the RISC-V specifications include one real-time timer for the use of the operating system in the core. Now that's been delegated really to the platform level, meaning outside the core, that's fine, but still you have one. And so what you should run 3 operating systems, each one in one zone, while Multizone provides soft timers. And this is the way you can run as many operating systems or applications that extend the required time in there. The last group is really a high-performance version of trap and emulation. As you understand now, the system is secure, runs in user mode, but I told you it runs unmodified binaries. So what if your binaries assume they are running in machine mode, meaning highest level privilege like FreeRTOS? Do you have to rewrite your code? No, absolutely not, right? So the system traps and emulates, and for instance, read-only of some of these registers just goes on just fine. There is a little bit of an impact in terms of performance there. Trap and emulation is a bit expensive. If you go directly with the C library, that's a little bit faster. It's entirely optional. You can just go with straight, plain assembly, and it works just fine. And with that theme, I will pass back to you.
Okay, thank you very much, Cesare. So, last year we made an architectural announcement of PolarFire SoC. I just wanted to give you a quick overview on what this is, because it is germane to, security, real-time and Linux running on the same chip, and running a multi-zone type of microkernel on the chips. So PolarFire SoC is an SoC FPGA. What an SoC FPGA is an FPGA with a monolithic piece of silicon for the processor subsystem implemented as an ASIC block. So everything you see in the the gray boxes is an ASIC block, and it's a 5-core processor subsystem. 4 cores can run Linux. 1 core is a monitor core. You can imagine that monitor core, executing in its own separate zone or multiple zones within that core as a trusted execution environment. All these cores are deterministic amongst each other. We have a very interesting L2 memory subsystem, which we'll talk about in a minute. We get an integrated DDR controller, and we have fabric interfaces going in and out of this central AMBA switch that has memory protection built in and quality of service. So PolarFire SoC FPGA is kind of like a Swiss Army knife in your toolbox. It's got an FPGA. You can implement custom IP in it, and it's got a processor subsystem in it. And it has to serve many applications. It's not a specific product for a specific application. So we see a lot of requirements for running a rich operating system and a real-time operating system all on the same CPU. And that's what PolarFire SoC does. Now, if we go to the next slide, we can talk a little bit about how we enabled real-time and Linux to kind of coexist in a coherent CPU cluster. So the definition of real-time is, first order is determinism. I have to perform some task deterministically every time, on time, all the time, okay? And you really can't do that with an application processor. They weren't designed to do that. So how do you do that? What do we do? Well, we can actually turn off the branch predictors in any of these cores. You can either do it at boot, or you can do it as you enter the interrupt service routine. That way your branch history doesn't, of your main application doesn't, I would say, affect any code that is running in your interrupt service routine. The L1 memory subsystem in the CPUs can also be configured to be a tightly integrated memory, so you can have local deterministic zero-way access to those memories. And the L2 memory subsystem can be configured in 3 different ways. It can be a cache, it could be what we call a direct access memory, or it could be a coherent buffer. Because at the end of the day, if you have a rich operating system and a real-time function operating in the same CPU cluster, they're going to have to share messages back and forth, and you want those messages to be coherent, otherwise it'll lead to software bugs. So the L2 memory subsystem is very flexible, and the CPUs are very flexible that enable real-time performance, and the result you get is determinism. So if we can do one click, we've actually benchmarked this, and what you see there, that flat line, is the amount of CPU cycles that are consumed in an interrupt service routine. It's a synthetic benchmark. So we have on the 4 cores, we have synthetic applications running, trashing, the L2 cache memory, and then in the real-time core, the E51, we've got another application that's just reading and writing that memory, executing its functions, and interrupts are firing periodically. And you can see that for every interrupt routine, we actually compute the same number of CPU cycles. So we have determinism built into this processor subsystem. Now, so we have, Cesare talked about PMPs, physical memory protection, allows you to isolate and allocate certain memory regions to certain cores to be read-write executable, or read-write cacheable. And these are all isolation techniques that also have a kind of a security overlay to them. We also have a lot of security built into our platform as well. And if we go to the next slide, PolarFire SoC has been built on top of the PolarFire FPGA platform. So you got to program our FPGA. It's a non-volatile FPGA, so it powers up instantly. You program it once, and it just powers up like an ASIC. And when you program it, the bit streams are relatively large, 16, 32 megabits. They're all encrypted, and the programming methodology is DPA resistant. It's DPA resistant by protocol. So we roll the keys every n number of K bits so that we don't leak side channel information. We have anti-tamper detectors, voltage, clock, active mesh, temperature. We can offer a cryptographically bound supply chain assurance. We actually embed into our chip an X.509 certificate that is signed by our HSMs, which we use. HSM is a hardware security module, which we use during wafer manufacturing and package test. Okay, we integrate a physically unclonable function, which is kind of like a silicon fingerprint. It's kind of the ultimate in key storage. Only the chip knows the key, so it can be a root key for building up key trees and higher level protocols. And the good thing about that is, only the chip knows. No humans know. And usually humans are the weakest link in any kind of security process, function, or method. Got a built-in true random number generator. You can't build secure protocols without it. And on some devices, we have a side channel resistant crypto coprocessor that can do symmetric, asymmetric crypto algorithms. So that's what's in PolarFire FPGA. PolarFire SoC has all of that, and of course we've integrated secure boot. And we chose an architecture that's 5-stage pipeline, which in order execution, not out of order. So it's a deterministic core that is not subject to Spectre and meltdown attacks because of the nature of the architecture. And the physical memory protection, as Cesare alluded to earlier. And we have error correction on all the memories. Typically it's a reliability function, but it really is germane to security as well. So any kind of memory we will correct single bits and detect 2-bit errors. And these error signals are actually brought to the FPGA fabric so that you could do something with them in your logic, because at that point in time, if you get a 2-bit error in some memory that may contain your stack, your system becomes unreliable and unstable. So we take all our inputs from DoD. Microchip is the #1 supplier of silicon components to the Department of Defense. We take security seriously, and PolarFire SoC is going to be a great secure SoC FPGA platform. So if you want to learn more about Multizone, you can go to Hex-Fi's website, or you can contact them at that email address. Likewise, for PolarFire SoC, there's a link built in here. Or you can just Google PolarFire SoC, or you can send an email to polarfiresoc@microchip.com. I'll get it. As a reminder, October 23rd, we're going to be doing a Microchip Trust platform for crypto authentication. November 6th will be protecting your IP in a cloud-connected world, and December 4th will be another RISC-V topic, RISC-V enclaves, a clean slate approach to Linux security. And we'll be at the RISC-V Summit in December in the San Jose, California area. And this is the second annual RISC-V Summit. Hex-5 will be in the Microchip booth, and we'll be showing off what we've discussed today and other demonstrations of things that are going to be running on PolarFire SoC.